discussing the unit number 6, arenes and aromaticity of organic chemistry. Last time in this unit we have discussed synthesis and reactions of alkyl benzenes. Now today we are going to discuss alkenyl benzenes which are conjugated to benzene ring. We will discuss their preparation, reactions and then synthesis of biphenyls and their reactions, and then finally we will discuss mercuration of benzene. Now we start with alkenyl benzenes. First, preparation of alkenyl benzenes which are conjugated to benzene ring. First method, dehydrogenation. By dehydrogenation of ethyl benzene at 600 degree C in presence of a catalyst chromium oxide and aluminium oxide, we get this dehydrogenation and the final compound is styrene. This ethyl benzene can be synthesized by Friedel-Crafts reaction of benzene with ethene in presence of phosphoric acid. Now second method is dehydrohalogenation. If we have in a side chain halogen substitution, like if we have 1-chloro-1-phenylethane, then by heating with alcoholic KOH, there is a dehydrohalogenation and we get double bond in the side chain. This compound can be synthesized by chlorination in presence of UV light of ethyl benzene and we get this substitution at first position. It is a major product here. Third method is dehydration. Dehydration takes place in presence of acid. So, acid can be sulfuric acid. So, this can be done only when alcoholic group is present in the side chain. So, in presence of a acid there is a dehydration and we get the double bond in the side chain, and this compound can be prepared by reaction of a Grignard reagent, phenyl magnesium bromide with acid aldehyde. Now, if we have 2-chloro, this 3-phenyl propane, or we have a 2-hydroxy or we can say 3-phenyl 2-propanol, then there are two possibilities for here dehydrohalogenation. Hydrogen can be removed from this methyl group or from this CH2 group, but it was observed that it is removed from this CH2 group and there is a formation of 1-phenyl propene instead of 3-phenyl propene. Similarly, here also in case of alcohol there is a dehydration and for dehydration hydrogen comes from this CH2 not from this CH3, and again there is a formation of 1-phenyl propene and not 3-phenyl propene, because here in 1-phenyl propene this double bond is in conjugation with this phenyl ring, and when double bond is in conjugation with phenyl ring, this compound is more stable as compared to this 3-phenyl propene or we can say allyl benzene. Now 3-phenyl propene is rapidly converted into 1-phenyl propene by treatment with hot alkali, and again the reason is same, because this 1-phenyl propene is more stable than 3-phenyl propene. So, that is why 3-phenyl propene rearranges to give 1-phenyl propene. Now, another method is decarboxylation of cinnamic acid. So, when cinnamic acid is heated with a small amount of quinol, this carboxylic group is removed in the form of carbon dioxide and we get the styrene. Now, reactions of conjugated alkenyl benzenes. Now, we have seen in alkenyl benzenes we have a unsaturation in side chain and we have a unsaturation in benzene ring also. So, both ring and double bonds are good source of electrons. So, there is a competition between a ring and side chain for electrophilic reagent, but we have observed that double bond shows higher reactivity than the resonance stabilized benzene rings. For example, in hydrogenation both side chain and this benzene ring get catalytically reduced or hydrogenated, for example in presence of hydrogen and nickel, but for side chain hydrogenation we need milder conditions, while for hydrogenation of benzene ring strong conditions are required. Similarly, for oxidation also, if we do oxidation of a side chain then milder conditions are required. hydrogen peroxide and formic acid to give diol, but if we use strong conditions, then there is a cleavage of carbon-carbon bond and final product benzoic acid will be obtained. Now, halogenation. Both double bonds and ring reacts with halogens by heterolytic mechanism, but first halogenation of side chain takes place. So, once the saturation of side chain takes place, then only halogenation of ring takes place. For example, if we want to prepare para-bromostyrene, so if we do direct bromination of styrene, then instead of getting ring bromination, first we get bromination in side chain, and this is even under a mild condition in presence of CCl4, this takes place. So, we will not get this para-bromo, instead we get the side chain bromination. Now, if we want to prepare para-bromostyrene, then we have to start with ethyl benzene. Now, here there is no double bond in the side chain. So, if we do the halogenation with bromine and ferric bromine, then there is a para-bromo ethyl benzene get formed, because we had here we get ethyl group is ortho and para directive. So, it gives a mixture of ortho and para-bromo. So, we take para-bromo ethyl benzene and then we introduce double bond in the side chain. So, for this we do the bromination in presence of H mu light or heating. So, side chain bromination takes place and then dehydrohalogenation with alcoholic KOH. So, we get double bond here. So, in this way we can prepare para-bromostyrene. Now, next is addition of HBr. Now, addition of HBr we will discuss two cases, in absence of peroxide and in presence of peroxide. So, in absence of peroxide it is a normal reaction, it is a electrophilic addition reaction. So, first there is a addition of H plus. Now, there are two CH and this CH. So, H plus can add to this carbon or this carbon, but it was observed that hydrogen goes to this carbon, and due to this which we get the benzyl cation, because this benzyl cation is more stable. This positive charge is in conjugation with benzene ring, so it gets stabilized more and then attack of a nucleophile and we get this bromo substitution. Now, if we do reaction of HBr in presence of peroxide, so there is a generation of first bromine free radical. Now, again bromine free radical can attack on this carbon, double bonded this carbon or this carbon, but it was observed that this bromine free radical attack on this carbon. Because of this, there is a free radical form on this carbon which is a benzylic carbon, and this free radical again is stabilized by this benzene ring. So, that is why it is more stable and it will get formed, and which takes H free radical from HBr to give the substituted product. Now, if we compare the reaction of HBr with alkynyl benzenes and simple alkenes, it was observed that alkynyl benzenes are more reactive than simple alkenes, because the conjugated alkynyl benzenes are more stable. This indicates that alkenes should be more reactive than alkynyl benzenes, but observation is that conjugated alkynyl benzenes are more reactive than simple alkenes. The reason behind is that stabilization of transition state in case of alkynyl benzene is more as compared to stabilization of reactant. That we can discuss by taking this potential energy curve. This A curve is for conjugated alkynyl benzene and this B is for simple alkene. Now, we can see this is a stabilization of reactant, this is a stabilization of this alkynyl benzene is more stable than alkene, but this energy difference is less as compared to the stability of transition state. The transition state is more stabilized in case of alkynyl benzene. So, net result is less energy is needed in case of alkynyl benzene, and that is why alkynyl benzene, conjugated alkynyl benzenes are more reactive than alkenes towards HBr reactions. Now, next molecule is biphenyls. Biphenyls, here two benzene rings are linked together. This biphenyl occur in coal tar and it is having a melting point 71 degrees C. Now, synthesis of these biphenyls via Fittig reaction, it is a reaction of bromobenzene with sodium in ether and we get this biphenyl and HBr. Another method is a reaction of bromobenzene in alkaline medium on refluxing with hydrazine and palladium catalyst on a calcium carbonate support produces biphenyl. Now, next method is by making use of benzene diazonium sulfate. So, when benzene diazonium sulfate is treated in ethanol with copper powder, then there is a formation of biphenyl. Next one is by making use of benzidine. So, in benzidine, if we remove this NH2 groups, then we get this biphenyl and this can be done via diazotization. So, first diazotization to prepare a diazonium salt and then this replacement of this diazonium group by hydrogen by using hypophosphorus acid. Now, next reaction is Ullmann bi-aryl synthesis. When iodobenzene is heated with copper powder in a sealed tube, biphenyl get produced. If we take aryl chloride and aryl bromides, then there is a necessary condition. In a ring, there should be electron withdrawing group present on ortho or para position of halogen atom. So, if we take orthochloronitrobenzene and treat with copper, then there is a formation of a biphenyl 2,2-dinitro-biphenyl. Now, next preparation is via Grignard reagent. So, phenyl magnesium bromide is taken, then it reacts with bromobenzene in presence of cobaltous chloride to give biphenyl. Now, industrial method. If we pass benzene vapors through a red hot tube at 600 to 800 degrees C, then there is a production of biphenyl. These biphenyls have major use as a heat transfer medium and chlorinated biphenyls are used as plasticizer commercially. Now, the reactions of biphenyls. So, as we have seen, biphenyls have two benzene rings joined together. So, these undergo electrophilic substitution reactions. One phenyl group behave as a electron releasing and other as a electron acceptor group. First substituent, if we do the electrophilic substitution, so first substituent enters mainly at 4th position and the second substituent enter in the second ring which is unsubstituted at para or ortho position. For example, if we take the case of nitration, main product for mono substitution is 4-nitrobiphenyl with a very small amount of 2-nitrobiphenyl and further nitration gives 4,4-dinitro-biphenyl and some amount of 2,4- and 2,2-dinitro-biphenyls, and similar behavior is observed for halogenation and sulfonation also. Now, next we discuss how this second substitution enters in this unsubstituted benzene ring. So, if we see the resonating structures of nitrobiphenyl, then we observe the positive charge is coming on ortho and para of this second ring. Then how this second substitution takes place on ortho and para position. For that, to see how this second substitution takes place in second ring at ortho and para, let us discuss the carbocation formed by para attack and meta attack. So, first we see by attack of this nitro group at para position, this carbocation get formed and this positive charge is stabilized by delocalization in this ring and in this ring also. But if we see the meta substitution, then attack at meta position and this carbocation, the positive charge is stabilized only in this benzene ring. So, carbocation is more stabilized in case of para as compared to in case of meta. So, that is why the attack takes place at ortho and para of second ring. Now, next reaction is oxidation. On oxidation, there is a small amount of benzoic acid formed and major amount is carbon dioxide and water, which get formed by complete oxidation of biphenyls. On ozonolysis at -20°C, it gives major product benzoic acid. Now, when we have discussed in last lecture substitution of benzene, electrophilic substitution in benzene, then we are left with mercuration. So, when one hydrogen of benzene is replaced by mercury acid group, then that is known as mercuration, and most common group is acetoxy mercury group, and this can be introduced by reaction of mercuric acetate or with mercuric oxide in glacial acetic acid at 90 to 160°C, and we get the product phenyl mercury acetate. We can also introduce this mercury nitrate group also, which can be formed by heating benzene with mercury nitrate in presence of mercuric oxide. So, this mercuric oxide is used to remove this nitric acid, since this reaction is reversible reaction. Now, today we have discussed the preparation of alkynyl benzenes, in which double bond is conjugated with benzene ring by taking different methods, which includes dehydrogenation, dehydration, dehydrohalogenation and decarboxylation. And further we discussed the reactions of alkynyl benzene, and we have seen that the side chain double bond undergo more rapidly reactions as compared to benzene ring. Then we discuss biphenyls, the synthesis of biphenyls by taking Fittig reaction, Ullmann reaction via disonium salt and via Grignard reagents. And we discuss also the electrophilic substitution reactions of biphenyls. So, in this biphenyls we have seen that one phenyl ring is acting as a electron acceptor and another is as a electron donor. In the last we have discussed mercuration of benzene, which we left in the last lectures, in which we have discussed the electrophilic substitution of benzene, and this is the last lecture of the unit also, arenes and aromaticity. Thank you.